So our bodies use ATP kind of like energy arcade tokens. So you can take energy from all sorts of different sources and convert them into this arcade token of ATP that can then be cashed in a bunch of different circumstances. No matter where that energy originally came from, now it's all ATP. So molecules like enzymes can specialize in using that ATP to make reactions happen. And ATP is going to help provide energy because ATP is holding a lot of energy. So those ATP, the triphosphates, we'll get much more into this, but those triphosphates are these negatively charged groups. And you have three of them that are tightly held together. When you have negative charges close together, they're going to repel from one another, but they have bonds that are holding them together. It's kind of like a clamp spring. So if you have a spring and you have to put in energy to clamp it, hold it clamped together. But when you release it, well, now if you had, say, a pinball or at one end or whatever, and you released it, now that thing would that ball at the end of the spring would then shoot across the room. But instead of that happening, we can channel what's happening here is similar in the chemical sense that you're releasing energy, but we're going to channel that energy into helping drive reactions. And so that's the basic of how this all works, but let's look a little more into the details. Why ATP? What's so special about ATP? How do our cells actually channel that energy? And why are we getting this energy out? And so let us look in closer detail.
So what is ATP? So ATP is just one of our RNA letters. So it's the A in the AT or AUCG in RNA. And the important thing for ATP as energy is really this triphosphate group. And so you might be wondering, okay, all of these different nucleotides, so all of these different RNA letters have that triphosphate group, at least in their triphosphate form. So why ATP? And it doesn't seem that there's a really good reason for why ATP, as opposed to GTP or CTP or UTP. And I'll actually get into a little later how our cells actually use GTP for some purposes like translation, and we use UTP or UDP for glycosylation, so adding sugar. So we do have other uses for these. And by kind of compartmentalizing the different nucleotides for different purposes, that's going to allow your cells to regulate them independently. So you're not glycosylating a bunch of stuff because you have a bunch of energy going on. And for the G proteins, so the GTP, it's also used in signaling, and you wouldn't want to have a bunch of signaling just happen because you have a bunch of ATP because you have a bunch of energy. And so it doesn't seem like there's a really good answer for why ATP. It's probably evolution, just kind of the first things started using ATP, and then everything kind of adapted to be specific to use ATP. And so then everything that was made off of that was made using ATP, and it kind of founder effect type of thing in the evolutionary sense. ATP and GTP, those are the two main ones that we use for energy. And you can see that these also are the ones that are these purines. So they have these two groups, these two rings as opposed to just one, and they have more potential surface that enzymes and other molecules that use ATP or that bind to ATP. There's more kind of different things so that they can have a more specific binding potentially. So those are just some of the thoughts, but it's not entirely clear that there's a real good answer, but it's probably largely an evolutionary thing. And then once it started, then it made sense for our cells to specialize in just using ATP mainly for the energy source. Because the really great thing about having this one thing is that you can use it in all sorts of different reactions. So also, no matter where your energy originally comes from, so there are a lot of ways that our cells can convert things into ATP. Various metabolic routes. So metabolism refers to the making and breaking of molecules. And so we have anabolism, which is molecule making, and catabolism, which is molecule breaking. And this catabolism is often done to generate ATP, such as with cellular respiration, where you get that really big payouts comes from oxidative phosphorylation, where you have this ATP it's going to make this ATP. So you can take energy from a bunch of different sources and get it to ATP, which is really awesome because then you can have all of these different molecules that are all going to use ATP, and now they don't care where that energy originally came from. So, but how does this ATP actually get like cashed in? How do we use it? So as I mentioned, those three phosphate groups, you have three phosphate groups, negatively charged phosphate groups. And this negative charge, when you have negatively charged molecules held close together, they're not going to want to hang out together. They're going to repel one another. And if they're repelling one another, then it's going to take energy to hold them together. And there's this thing called the first principle of thermodynamics, or the first law of thermodynamics, which says that energy can't be created or destroyed, it can only change forms and move. So if you're having to spend energy to clamp it or to hold those phosphate groups together, then you're going to get energy back if you break them apart. So it's just a law of thermodynamics. So we're going to get energy. We can represent this energy with this thing called delta G, this is the Gibbs free energy. We'll talk more about where this energy comes from in a minute, but if you have a higher Gibbs free energy, this is going to be like a less stable state, and this is going to be a more stable state. And this is going to be higher energy, and this is going to be lower energy. A reaction is going to be what we call spontaneous if you go from a high energy to a low energy. And so you might be wondering, okay, well, why doesn't this just happen randomly? Like, why doesn't it just fly off? And there are a couple of reasons. And so one of the reasons is that you have, although it's looks like, oh, you could just roll that ball down the hill, that's easy, right? Well, typically, there's actually, when you see one of these, you're looking at the beginning and the end. It's a state function. This delta G is what we call a state function. So it doesn't care what is happening in between, going from the initial state to the final state, just the difference in the energy between the states. But in order to get from one to another, you have to go up a ramp. And so there's an activation energy for the reaction to happen. And so this is good because our ATP is not going to just like split apart randomly. And even another thing that's really important is that in our cells, although we talk about like ATP, ATP is really going to be in complex with magnesium. So magnesium, it's a cation, so a positively charged, and then we have the phosphates, which are negatively charged. And so we talked about how these negative charges are repelling one another. But what happens is you have this positive charge, and now this is kind of helping hold things together. Metals like magnesium are really great because they can form these like coordinate covalent bonds. So they can form multiple bonds to things. And so they can kind of like help hold this together and keep it all calm. Okay, so, but you still have this much better, the products are still going to be much more favorable energetically than your reactants, than your initial ATP. And there are a few reasons why, and they has to do with various reasons. So one is entropy. So let's talk about where the delta G comes from. Delta G is going to come from entropy, which is randomness or disorder, as well as enthalpy, which is the energy of the bonds. When you have ADP plus PI, so this orthophosphate, when you have this, you have an entropy benefit because you've gone from having this single molecule to having two molecules. When you go from one to two things, well, now you're increasing this randomness, you're increasing this like disorder, this entropy. So one way to think about entropy is like the number of different states that something can occupy. So if you were to look at a single molecule, you could be like, going like this, blah, 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 blah. Or I guess, I don't know. I don't have a good example in hand. Okay, I have a screwdriver. That's all I have. Okay, so think about if my screwdriver is attached to my arm, it can move around. So they can have some like entropy. But what if they were separated? Now these can be moving around separately. And so if I were to look at them at any point in time, there would be a lot of more different states that they could be in. So it would seem to have more randomness or disorder. And so that's the idea with entropy. And so if you have these two molecules instead of just one molecule, well, now you have an increase in your entropy because you have more molecules out of it. You also are going to have greater resonance stabilization. So resonance is basically when you have like the electrons that are shared are going to be shared by multiple atoms. And so I'm not going to get too much into it here, but basically all of those bonds that you see, all those lines in the diagram, come from those atoms sharing pairs of electrons. And normally you have like two atoms sharing a pair of electrons, and we call it just like a covalent bond. If they're sharing two pairs, and we call it a double bond. Sometimes what you see is you have something called resonance, where you have multiple atoms, more than two atoms that are all sharing in this electron, like an electronic commune. And this makes molecules really happy. And so when we think about molecules being happy, we think about lower energy. And so you're going to have a happier state in this ADP and this with the phosphate, where you have this resonance going on, as opposed to in the ATP. Okay, you're also going to have better hydration. And so when we think about that ATP and the ADP, well, now they're going to be surrounded by more water molecules. They're going to be better hydrated. When this happens, you're going to get a lot of these water molecule interactions. And so although these aren't covalent bonds, these are just like hydrogen bonding, and these are more like strong attractions than actual like covalent bonds. They're not actually sharing electrons, but they are still like bonding, and it's in the sense of they give us an enthalpy benefit. And when we have this enthalpy benefit, that is going to further make this make this a more negative delta G, so a more favorable reaction. And it's the net balance of these. So you're going to have to put in some energy in order to break the bond. That is going to have to be true for no matter what bonds. You're going to have to put in a little bit of energy, because it's going to be an enthalpic cost in order to break that bond. So you're going to have to actually pay to break that ATP bond, but you're going to get back way more than you put in. And so an example of this is when we talked about the other day about why instant cold packs are cold, and instant hot packs are hot, and it has to do with the differences in how much energy it takes to break the bonds and how much energy you have in the new bonds, as well as the entropy. And so I'm not going to get into that here, but check out that other post if you want to know more. So often what are we doing with this energy? We're often using it to drive reactions, and often in the case, in some sort of with the help of enzymes. So enzymes are reaction catalysts. They speed up reactions. So they make reactions go faster. And the way that they do this, and they do this without getting used up themselves in the process, so they can do it over and over and over again. They're really, really cool. They're typically proteins, sometimes protein RNA complexes, sometimes RNA alone. In that case, we call them ribosomes, which is a cool word. And the ribosome is actually a ribozyme, but it also has protein too, but I'm not going to get into that. But anyway, how these enzymes work is they actually lower the activation barrier. So remember, we talked about the delta G and how it's a state function. So it depends on the initial state and the final state, like so the reactants and the products. So this would be like our ATP and our ADP. This would be our ADP and our PI. And so we didn't care what actually happened in between, just the difference. Well, in that we had this like barrier that we had to get over. Enzymes work by helping lower that activation barrier, and they can provide like an alternate route from one to the other. But because the delta G is just going to depend on the initial things, it's not going to care what's happening over here, but this is going to impact how fast the reaction is going to go. So enzymes often use ATP to help make reactions happen. And so how is this actually going to be happening? Okay, so first of all, we can add different parts of ATP onto things. So we can have, in addition to ATP, we can like add AMP, we can add ADP, we can break and we can make, and we can do all sorts, add single phosphate groups. There are a bunch of different ways that you can use ATP. And one of the reasons why cells will add AMP or ADP or something to a reaction, why they'll use ATP, is because the phosphate groups serve as really good leaving groups. So a leaving group, basically what happens is you can get something called nucleophilic substitution, where you have one molecule, which is a nucleophile. So it's something that once it has extra electrons, so it wants protons. And so protons, you think nucleus, nucleophile. So these are molecules that want more positivity, want to share those electrons. And then they make a perfect pair with an electrophile, which is something that wants more electrons. And so the phosphate, the P and the phosphate, that phosphorus in those phosphate groups, it's actually going to be electrophilic. And so often we think about electrophilic things as being like positive charge, but it turns out that P is actually kind of positive charge, even though these phosphate groups are negatively charged. What's happening is that oxygen is really what we call electronegative, which means it's hogging those shared electrons. This is going to make the P partly positive. If it's partly positive, and now it's going to be electrophilic and is subject to attack by a nucleophile. If you have it subject to attack by a nucleophile, when the nucleophile attacks it, well, now you're going to have too many things bound to that phosphorus. And so something is going to get removed, and you can have the thing removed. If you have your leaving group, the better the leaving group, the happier this thing is on its own, the more likely this is to happen and to be stable and happy. And so those phosphate groups, as we talked about, those are going to be really good, really happy on their own. So they're going to be really good leaving groups. So by adding some sort of ATP derivative onto something that we want, we can then make it more likely that that the reaction will then react there, because now you have a better leaving group than what you originally had. So here's an example when we have amino acid activation. So we have an amino acid, and this is part of so in translation, when we're making proteins by linking together amino acids with the help of the ribosome. In order to bring those amino acids, you bring them with these tRNAs, and you have to add the amino acid onto the conjugate, or you have to add that amino acid onto the cognate tRNA. So basically the tRNA that has the anticodon that corresponds to the codon. So I'm not going to go into all that here. If that made sense, great. If not, check out my content on this. But the basic idea is that you can add, you use the energy from the ATP, you break that bond, you add on AMP to this amino acid. Now what this is going to do is you've provided a better leaving group. So our goal is to get this added onto this. And what's going to happen is that this oxygen is going to attack this carbonyl carbon. OH isn't that great of a leaving group, and so, but AMP would be a really great leaving group. And so by initially doing this charging step where you're adding on the AMP, now you're making a much better leaving group, so that when this goes to attack, now it's attacking this carbon and you're getting this AMP leaving, which is going to be a much better leaving group, and this is going to be a much more favorable bond to break. And so this is an example of how we can harness that energy from ATP in order to make sure that this reaction goes right. So additionally, we're like directing it to where we want it to attack, and we are helping making that attack more favorable. Another thing is when you break, so here we're adding AMP instead of ATP. When we do this, what we're doing is now you get this pyrophosphate, which is these two phosphate groups, which then you have like pyrophosphatase. So basically these can get broken up by with the help of another enzyme, and then you get even more benefit. You get a bigger boost because now you're having entropy benefit from having two of these, and you're having better, like you have all those hydration and things. So you're going to get a lot more energy benefit out of this as well. You also see a lot of phosphorylation. So this is where you just get a single phosphate group added, and this is going to help. Phosphorylation is done by like enzymes called kinases, and when you add just a single phosphate group, now you're still getting that leaving group benefit, and you're also, this is another way where you can direct enzymes to specific sites. So by using one enzyme that's specific for phosphorylating one site, so say it recognizes the molecule and it says, okay, I'm going to put a phosphate group right there. And then this other molecule can come along, recognize that, and then act accordingly. Yeah. So you can be directing things to where you want it to go. Also by having like charging an ATP, you're also kind of making it more, by making it energetically unfavorable, like so that like you have to put that cost in up front. And that can make it so that reactions, you don't want reactions to happen when you don't need them to happen. And so this offers a way of regulation as well as the kind of like confirmation step that you want to move forward with the reaction. So much more on that in other posts. When we, going back to that idea of like the pyrophosphate and stuff like that. Okay, so in our DNA polymerase, when it links together DNA letters, and our DNA ligase, it seals gaps. And so looking at these two, they're both going to use a nucleotide triphosphate. And so here you can have any nucleotide triphosphate, but here you're actually going to use ATP, and this ATP is going to help make this reaction compatible, whereas here you're just having any old NTP. The reason why I bring this up is that it's actually when you have this polymerization happening, so when you have your DNA letters linking together, or the same when you have your RNA letters linking together, you have, this is going to be, you pay the cost for linking those together. So you pay that cost. Remember, now you're forming a bond. So you're decreasing the entropy. You have this NTP that's floating off freely around. It's really happy. And now you're going to be linking it up in this large chain. And so you have an entropy cost. But what happens is that you are breaking this bond, you're getting this pyrophosphate, which can then hydrolyze, and you get orthophosphate. And so you get this big energy benefit, and you have using this ATP or this NTP, this triphosphate groups. And the enzyme is going to help make that happen. So with the DNA ligase, though, here you have a broken chain, so you don't have that triphosphate group. When you don't have this, now you don't have the energy benefit. So you're not going to have that leaving group now. If this isn't going to really want to join into this, you don't have a good leaving group, you're losing the entropy, various things. So in ligation, the DNA ligase actually has to use ATP, and so that you get AMP attached, and then it's going to offer to the enzyme, and then this is going to attack from the enzyme and give you this back. And so the ligase is going to help use the power of ATP. And so that's just another example of how the energy from ATP can be harnessed. So we don't want ATP just like exploding itself in our cells. That wouldn't be good. Kind of like how you don't want fireworks to be going off all the time. And so we talked about how ATP is stabilized inside of cells, and how you do have some sort of activation barrier. So it's not just going off, but our cells also can tightly regulate the levels of ATP. And actually by regulating these levels, we can also, in addition to preventing things from going all off in our cells. So in addition to just, if it were to just like hydrolyze, to just like break apart because of water, you wouldn't want, if you had a bunch of ATP stocked up, then you wouldn't, but just because you have energy, then you wouldn't want it to be causing all these reactions to happen. And so our bodies actually, instead of storing a ton of ATP, they'll keep the energy in storage forms like storage sugars like glycogen. But we also keep pools of ATP as well as ADP. So that product of using the ATP, or at least one of the products of using the ATP, and our cells can regulate the levels of these in order to drive metabolism, catabolism, so breaking down molecules, and anabolism, so building up molecules. And there's various levels of regulation that can occur. And our muscles, because they don't want to have to wait around to break down glycogen and stuff, they actually keep some, like a stock of ATP in the form of phosphocreatine. So it's not really ATP, but they phosphorylate creatine. You get phosphocreatine. And this is going to, then when ATP levels are low, that phosphocreatine, the phosphate you just put on there, can get transferred back to ADP to give you ATP. So this will give you your muscles ATP in a hurry. Some cool stats on ATP. So this is from this For the Love of Enzymes, The Odyssey of Biochemist by Arthur Kornberg. Thank you to Dr. Alexander Newton, president of the IUBMB, for giving me that book a couple years ago, which I love. So an intake of 2,500 calories, which are actually kilocalories, corresponds to a turnover of about 180 kilograms or 400 pounds of ATP. But your body only holds about 50 grams or a tenth of a pound of ATP at a time. So in order to reach that 180, it has to be constantly turning it over. So like using that ATP. So that 50 grams gets turned over about 4,000 times per day, which is pretty crazy. And if we want to quantify things with molarity, so like copies of molecules, you can math it out and see that 50 grams of ATP is about 66 trillion molecules of ATP. So on average, that last phosphate, so that gamma phosphate, gets taken off and added back on 3 times per minute, which is a pretty amazing stat. So ATP is really, really awesome, but it's not the only NTP as we talked about. And so there are other uses for these. And the other one that we see a lot as energy source is GTP. So guanine triphosphate. And so one place that you'll see this is in signaling pathways. You have like G-coupled protein receptors or G-protein coupled receptors, those sorts of things that use GTP and GDP for energy signaling. You also have a lot of GTP being used for translation because a lot of energy that your body uses is for translation, and this energy for translation is coming from this uses GTP. And so you have several different steps in the translation process. You have GTP being used. So we saw how ATP was used to charge that tRNA, but then to actually bring that tRNA to the ribosome, you use a GTPase, and then you have another one that's going to help kind of move things over from the site and like shift things over in the ribosome so that the next tRNA has room to come in. So you'll see GTP being used in translation, and because you have to have these, like two of these factors are happening like every time you have to add a single amino acid, and a protein can have like thousands of amino acids. So you're using a lot of GTP. And then UTP or UDP is used. So UDP from UTP, basically UDP gets added on to sugar blocks, building blocks, that then get used to add sugar chains, so to glycosylate various proteins, lipids, et cetera, et cetera. And so you'll often see like UDP glucose or UDP something or another. That's going to help, as we talked about, similar to how we talked about before. It's going to provide like good leaving groups and direct things and all of that cool stuff. So there are other uses for, so your other nucleotides do play key roles outside of their function in just being used in our DNA or RNA. In these cases are RNA, although DNA letters are typically made from RNA letters by hydroxylating them. But anyway, not going to get into that there, but just biochemistry is really cool, and I hope that helps you better understand and appreciate ATP.